Example 12.2 defines a function using the equation f of x equals x squared minus 2x plus 3, and we're also told that the domain of this function will be all real numbers. The first item on the list is to graph f on a Cartesian coordinate plane. So when I look at f, one of the things that I might notice immediately is that there is this plus 3 here at the end. And so you might be very tempted to want to do a transformation where you shift the whole graph up by 3. But that would be an incorrect approach because this is not vertex form, this is the standard form. Fortunately, we have already developed the vertex form for this equation. We did that back on example 12.1a. So the vertex form equivalency to this would be f of x is equal to x minus 1 squared plus 2. There are three things that I want you to identify from the vertex form version of the equation. Number one, I want you to identify the vertex. Now, consequently, we already did that back in example 12.1, but it certainly doesn't hurt to write it down again. The vertex would be located at 1, 2. This is the most important point for the graph of your function. So let's go ahead and mark the point at 1, 2. The second thing that I want you to get from this is going to be coming from the value of a. So in this case, the value of a is implied to be 1. Since the value is positive, it's a positive 1, that means that our parabola is going to open up. So the second thing that you will do is decide whether it opens up or down. In this case, it opens up. And the third thing I want you to do is identify whether there is going to be a stretch or a shrink compared with the original parent function. So the threshold for stretching and shrinking is all around the value of 1. If something is greater than 1, vertical stretch. If our a value is less than 1 but greater than 0, we'll consider that to be a vertical shrink. In this case, since we have exactly 1 for our a value, that means that there is no stretch or shrink. We will not have either one of those going on. And that's good to know. So we have all the information we need now to be able to graph. You should go back and review the key points that go with the squaring function. If you don't know them, you need to know them now. So I'll go ahead and plot these points. And I will try to create my parabola shape. And since the domain is all real numbers, I know that this graph is going to go off to the left and right forever. And I will label this as f. You will also notice that there is a axis of symmetry, which is the vertical line that crosses through the vertex. And I'm not being asked to graph that, but it's just a good habit to get into of graphing the axis of symmetry so that way you can visualize where the symmetry is within your parabola. So let's move on to part B. Part B wants us to address the domain and the range for this function. Well, the domain was already given to us. The domain is going to be all real numbers. But the range is something that we need to look at on the graph. The range is going to have a low value of positive 2. So I'll put a hard bracket at 2. And since the parabola opens up, it's going to be unbounded going toward positive infinity. So we would say from 2 to positive infinity. For part C, we're looking at stating the intercepts for the graph of f. Now, when we talk about intercepts, there's always two types of intercepts. There's either x-intercepts or there is a y-intercept. Because the vertex is above the x-axis, and our graph ends up opening up, there is no way that it encounters the x-axis. So there are no x-intercepts. But for the y-intercept, we do have one located at 0, 3. And I don't have to go do a calculation of that because I was able to acquire the exact location 0, 3 from the way that I plotted the key points for my parabola on the graph. Part D is looking for the relative extrema. So for the relative extrema, there is always two types of those. There is a relative maximum, or there is a relative minimum. When we're dealing with a quadratic function, you will never have both. You will have one or the other. In this case, the vertex ends up being located at the relative minimum. So I will write none for relative max. Relative min, I will just write down the ordered pair 1, 2, which is representative of the vertex. So the vertex is a very important point. It helps us to determine the range, and it also tells us about the relative extrema. Part E. In Part E, it says to state the intervals of increasing and decreasing behavior. The vertex, once again, is a very busy point, a very important point, and the axis of symmetry as well helps us to visualize where we have a change in behavior. Everything to the left of the axis of symmetry has a decreasing behavior, and then the curve to the right of the axis of symmetry has a increasing behavior. So we were going to say increasing occurs from 1 to infinity, and then decreasing occurs from negative infinity to 1. And the final part, part F, wants us to write an equation for the axis of symmetry of the graph of F. So I'm going to abbreviate that AOS. And the axis of symmetry is that vertical dashed line, the red one that we have here, and it would take on the equation x equals 1. So the example that we've just completed had us perform the graphing first, and then we used the graph to help drive the rest of the analysis of the function. Now that may not always be the appropriate way to do it. You may find that in an example, graphing is really difficult to do, and so the analysis needs to be done first, and then you can use the results of the analysis to actually help you get the graph completed that way. So we will see examples of both throughout this section.